Hi students, welcome to Max Point of View. Today we are going to solve each and every theory question from the chapter Magnetic Effect of Electric Current, that is part A of Electromagnetism. Before watching this video, my suggestion is watch the concept video first so that you will understand the concept, then you can apply this here along with me. Or else most of the topic which we are going to discuss today will be really confusing for you. So without wasting any time, we'll start with our first question. Our first question, how is the magnetic field due to straight current carrying wire affected if the current in the wire is decreased and reversed? There are two sub questions. First, listen here, we need to understand the concept. In the concept video only we have understood all these things. Here also I am going to explain. Current is directly proportional to magnetic field. Okay, what do you mean by that? If you increase the magnitude of current, that is nothing but the value of current, magnetic field or magnetic strength also increases. If you decrease the value of current, magnetic strength also decreases. And if you change the polarity, that we are going to see in the second sub question. Now listen, A. So what happens if you current in the wire is decreased? That is nothing but the value of current is decreased. If the value of current is decreased, magnetic strength or magnetic field also decreases, because those two are directly proportional. If current increases, magnetic field also increases. But here they are talking about decreasing the current. So magnetic field. Okay, you don't have to write magnetic field also, because they are talking about magnetic field only. You can just write decreases. See, these are the answers you are going to write in the exam. In the exam, you don't have to write in the complete sentence. As an evaluator, I will be looking only for the keyword, the proper answer. So you don't have to write it in the form of sentence. Like most of the students while correcting the papers will be like finding the exact word. They will write, if you decrease the value of current, the magnetic field also decreases. All those things not required. The required answer is decreases, because we know we are going to decrease the value of current, because that is in the question, and we are definitely talking about magnetic field. You don't have to write it in the form of sentence. This is enough. Next, if you reverse the current direction, that means assume there is a circuit. Don't worry about any incomplete circuit. Assume this is the current we are getting from the cell. Okay, if you change the direction of this one like this, okay, like this, what happens to magnetic field? This is their question. So if you do like this, the direction of magnetic field also changes. So if you reverse the current, what happens to magnetic field? The direction of magnetic field also reversed. Okay, and you should not write short forms in the exam. How many short forms you are going to write, that many marks you are going to lose. Okay, assume in a question you have written 3 short forms, they will deduct 1 mark. In a separate question, again you have used a short form, they are going to deduct mark. So my suggestion is never ever use any short form in the exam. Our second question, a straight wire lying in a horizontal plane. This is very much important. Horizontal plane carries a current from north to south. What will be the direction of magnetic field at a point just underneath it? That means if the magnetic this needle is just below the wire, see that the important word is the magnetic needle is below it. Okay, so whatever we are learning, it is just all for below. And if they ask the same question, like if the magnetic needle is just above it, then whatever we are learning, it will be exactly opposite. This is what we have learnt in concept video. That's why my suggestion is always watch the concept video first, then come to the theory solution. After that, if we have numericals, we are going to solve each and every numerical from the textbook. So here See, if the direction diagram is given, then you can aramse write what is north to south. But here the problem is north, south, east, west. This is the direction we know, correct? But here they are talking about horizontal conductor, and the current is flowing from north to south. North is not in horizontal plane, it is in vertical plane, correct? So I have to reverse it like this. Okay, you have to reverse it like this. So assume, see, if you make it vertical, the top side is north and the bottom side is south, correct? So make it horizontal because they have told in horizontal. Okay, now here if they ask a diagram, then these kind of things will definitely help you. In this question they are not asking the diagram, they're just looking for the answer. See, we know these direction, north, south, east, west, correct? So they are talking about a conductor which is horizontal and a current is flowing from north to south. You can write this north this side and south this side also. Finally whatever we are going to do, that is very much important. Okay, see here, whenever the current, okay, current is flowing like this, current, see this thumb, always use right hand, to find the direction of magnetic field. Keep this in mind. See, to find the direction of magnetic field, we are not going to use any difficult law. It's a very simple law. It is right hand thumb rule. If you write right hand rule also, they are not going to give you marks. We are using right hand thumb rule. Okay, so here this thumb will shows the direction of current. So now, and always your palm, right hand palm, should be in front of you whenever you are finding the direction of magnetic field. This is what we have learnt in concept video. See, this palm should be always in front of you and you have to use right hand. This thumb represents direction of current. So this is the direction of current, correct? And this will be the direction of magnetic field. So if it is horizontal, we use it like this. If it is vertical, if the conductor is vertical, we will be use it like this. Okay, we'll be using like this. So keep this in mind. If the conductor is horizontal, we will be using like this. We will not fold these fingers. If it is vertical, we will fold it like this. Okay, now anyhow it is horizontal. Okay, because when it is vertical, we are not going to find whether it is east to west or west to east. Okay, we are going to find whether it is clockwise or anti-clockwise. That's why we are going to hold it like this when it is vertical. Now anyhow it is horizontal, we have to hold it like this. See, why we have to hold it like this? Why not like this? Because this represents the direction of current. Anyhow the current direction is like this, so you have to use it like this. And now where is the direction of magnetic field? This represents the direction of magnetic field. So see, now if you rotate it like this, the upward part will be east. So we are looking for upward part, correct? So the direction of magnetic field is towards up, and if you rotate north south like this, okay, the upside will be east. Some students, okay, the answer for this question is towards east. Okay, east. Towards east, you can write it as towards east. Some students, instead of taking north south, they will go like this. You can write it like this also, no issues. The same method. Okay, so here you have to hold the right hand according to the direction of current. So initially we used it like this because the direction of current was like this. Okay, now the direction of current is like this. So hold it like this, and always keep remember, okay, this palm should be in front of you and this thumb represents direction of current. So I have to hold it like this. Now see, if you hold it like this, so if you rotate like this, north will go that side, south will come this side. Okay, if you rotate it like this, okay, this east will go down, and this fingers will represent the direction of magnetic field. Again the answer is east only. So if you write like this or like this, answer will be east only always. These are the simple techniques which we are going to use to find the direction of current. The answer was just east only. The finding the method is very much important. This is what we have learnt in concept video. There is one more sub question. name the law, okay, which is used in part A. Very simple, I told you earlier only, it is right hand thumb rule, okay, right hand thumb rule. To find the direction of magnetic field, okay, because of the current, whenever there is a current, magnetic field will be produced. To find the direction of that magnetic field, which law we are going to use? Right hand thumb rule, not Fleming's right hand rule. It is just right hand thumb rule. Thumb, the word thumb is very much important. So if you just write thumb rule also, they are not going to give, okay, because there is no left hand thumb rule, okay. The only rule is right hand thumb rule for now, okay. There are many other names for the same thing, but that is not mentioned in the textbook, so don't worry about it. So it is right hand thumb rule. See, right is also important, thumb is also important. Our next question, a wire bent into a circle carries a current in anti-clockwise direction. What polarity does this phase of the coil exhibit? Okay, here the important thing is a normal wire, okay, a wire like this, okay, is bent into a circle like this, coil, okay. Now the current here is flowing in anti-clockwise direction. Anti-clockwise, so this is clockwise, right? Anti-clockwise direction. So what kind of polarity it is? See, it is very simple. This is what we have learnt in concept video. Anti-clockwise, it is always north. Keep this in mind. Anti-clockwise, it is always north. Clockwise, it is south, okay. Instead of the anti-clockwise, they can also use counterclockwise. It is the another name for anti-clockwise. Just clockwise is south, anti-clockwise or counterclockwise, it is north. So what is the answer for this question? That is north. That's it. Our next question, what is the direction of magnetic field at the center of the coil carrying current in clockwise direction and anti-clockwise direction? There are two sub questions. Listen, this is a very tricky question, not the direct question. See, what is the direction of magnetic field at the center of the coil? So first you need to understand what is a coil. Coil is nothing but which is circular in shape, okay. Coil, okay. Now listen, if you write it vertically, it is different, okay. Write it like this, a coil which is held horizontally, then you will understand a few words here. So now here, if the direction of current is clockwise, okay, if it is clockwise, then what is the direction of magnetic field at the center of the coil? See, this is very much important. Center of the coil means they are talking about axis. They are talking about axis of the coil. Okay, now listen, if it is clockwise, this is what you are going to write. If it is clockwise, okay, the direction of magnetic field is along the axis of the coil, the direction, all those things that is mentioned only. So you don't have to write all those things, along the axis, because they are talking about the center, exact center, along the axis of the coil, okay, inward. This is very much important. If it is clockwise, we know it is south, correct. We know it is south polarity, correct. Now if it is clockwise, you need to understand one more thing. The direction of magnetic field at the center, okay, will be inward. Then why we are using along the axis of the coil? Because this is not mentioned in the question, correct. Why we are mentioning in the answer? Because they are talking about center of the coil. Center of the coil is nothing but along the axis of the coil, inward. If it is clockwise, it is inward. If it is anti-clockwise, the same answer, along the axis of the coil, it is outward, okay. See, if it is clockwise, inward, anti-clockwise or counterclockwise, it is outward. Our next question, how is the magnetic field due to a solenoid carrying current affected if a soft iron bar is introduced inside the solenoid? Okay, a few students will fail to understand the question only. See, understanding these kind of questions are very much important. Listen, first they have a solenoid. Okay, this is nothing but the solenoid. Okay, now it is carrying some current. Okay, whatever the direction, don't worry about the direction. Okay, now inside this solenoid we know there is a huge gap, correct? So inside this they are going to introduce a soft iron. Inside that they are going to introduce a soft iron. Now the question is, what happens to the magnetic field? The answer is very simple. The magnetic field increases. Magnetic field, see, you don't have to write magnetic field will increases. Just increases is also fine. Will increases. Why? Because see, here they are not asking why, but we have to know the reason also. Very simple. See, because of this solenoid, okay, the current is flowing through it, magnetic field will be generated, correct? The magnetic field will be generated. That magnet, okay, the magnetic field magnetizes this soft iron. Why? Because whenever there is a magnetic field due to current, okay, it produces magnetic field, correct? It produces magnetic field, and the soft iron is a magnetic material. What do you mean by magnetic material? It gets attracted to magnet, okay, and that will be temporary. So see here, whenever this soft iron is introduced in a solenoid, magnetic field will be around it, okay, in 360 direction. So it will not get attracted because magnetic field will be pulling it in all the directions. So it will be at the center only, but it will be magnetized. Very simple. See, if you take a nail, iron nail, okay, iron nail, and attach it to magnet, so this iron nail will also convert it into temporary magnet, correct? In the same way, here this solenoid has a magnetic field due to current. This magnetic field will try to attract this soft iron, but it is in all directions, so it will not attract it. So magnetic field will be introduced in the soft iron also. So totally magnetic field increases. That's it. Our next question, name one device that uses electromagnet. There are many devices you can use. You can write any one. So in the textbook they have mentioned electric bell, loudspeakers, okay, electric motor, you know, MRI scanning, MRI machines, and even maglev train also. So any one you can write in the exam. Our next question, complete the following sentences. When current flows in a wire, it creates magnetic field. So not only just magnetic field around it, this is very much important. So whenever a current, okay, in a conductor is flowing in any direction, it creates magnetic field, but where it creates? Around it, everywhere, okay, on the top as well as bottom. So around it, it creates magnetic field around it. Our second sub question, on reversing the direction of current in a wire, the magnetic field produced by it gets reversed, because both are directly proportional. Next, a current carrying solenoid behaves like a, see, solenoid will be like this, correct? This is nothing but solenoid. So here whenever you pass a current through it, it creates a magnetic field, correct? But it behaves as a bar magnet. So the question here is, the current carrying solenoid behaves like a bar magnet. Keep this in mind. Okay. The last sub question, a current carrying solenoid when freely suspended, okay, if you suspend it like this, it always rests in dash direction, north south direction, because it behaves like a bar magnet. When you suspend a bar magnet freely, what happens? It always rests in north south direction. We know solenoid, okay, current carrying solenoid is nothing but not just solenoid. Current carrying solenoid, solenoid is just a conductor. Current carrying solenoid, it behaves like a bar magnet. So if you suspend it freely, it rests in north south direction. Write it in full form, north south direction. That's it. Our next question, State a law which determines the direction of magnetic field around a current carrying wire. See here they are not just asking you to name it, they are asking you to state it. State means define it. So which law we are talking about? Whenever we talk about finding the direction of magnetic field, it is always right hand thumb rule, nothing else. Okay, finding the direction of magnetic field, always right hand thumb rule. Now we have to state it. That is nothing but whenever current carrying conductor, okay, current carrying conductor, okay, held in a right hand, this thumb represents the direction of current and the fingers represents the direction of magnetic field lines. That's it. Our next question, what will happen to a compass needle when the compass is placed below a wire with a needle parallel to it and a current is made to flow through the wire? Give reason to justify your answer. See, very simple question. They are not asking about the direction, they are just asking what happens. First, here you need to understand the concept. Assume this is the conductor carrying current. Whenever this carries current, it produces magnetic field around it, everywhere, okay, around it. So now they are talking about keeping a magnetic needle below it and parallel to it, parallel and below. Now what happens to it? Because of the magnetic field produced by the current, see, this is the reason you are going to write, because of the magnetic field produced by the current carrying conductor deflects the compass, okay, compass, and it shows direction. That's it. Our next question, name and state the rule by which the polarity at the ends of a current carrying solenoid is determined. So that is nothing but how to find the direction of magnetic field in a current carrying conductor. Okay, that is nothing but solenoid here, and we have to name it and state it. See, the naming part, when you come to naming part, we just have to write the name. It is right hand thumb rule. Right hand thumb rule. How to define it? Just now in the first sub question, okay, of short questions, we have defined what is right hand thumb rule. Here also we'll discuss. Very simple. Whenever we hold a current carrying conductor in our right hand, the thumb represents the direction of current and the fingers represents the direction of magnetic field. That's it. Our next question, the diagram in the figure shows a small magnet placed near a solenoid AB with its north pole, okay, near to the end A. Current is switched on in the solenoid by pressing the key K. So there is a key called K. When you press it, there will be a current in the solenoid. Our first sub question, state the polarities at the ends A and B. So here what polarity? Polarity of magnets is nothing but north and south only. So we have to state which is north and which is south. This is what we have learnt in concept video. So here the important thing is the first line of the wire. The first line of the wire, is it above the rod? Okay, assume this is a wooden box, okay, wooden box or wooden rod. Okay, now this line, the line of wire, this first line of wire is whether it is above or below. See, if it is above, we have to hold it like this. This is what we have learnt in concept. So if it is above, we have to hold it like this. If the same diagram, everything is same, so the same box, the same wooden box, if this first wire is coming from the back side, so don't worry about the remaining part. The important thing is where is the first line. See here the first line is above the box, above the wooden box. Here the first line is behind. So if it is above, okay, the first is above, you have to hold it like this. If it is like this, if the first line is behind, you have to hold it like this. So it is coming from behind, here it is above the wooden box. So anyhow in this diagram, okay, it is above, you have to hold it like this. Now this term represents north sometime, south sometime. So how to identify? Very simple. If the plus is towards left, so this term represents north, in the same diagram. Okay, so answer for this question, A is north. Now first we will write the answer. Now the answer is done. Now I am going to change the polarity. Now if in this question, if I do some modification, okay, there is no modification in this question. I'm just teaching you in all angle. Okay, now the same method you have to hold it like this because the wire is okay above. Now once you hold it like this, now this term not represents north always, sometimes it will be south based on the direction of current. In the previous question, okay, in the original question, the plus was this side, that's why it was north. Now the plus is on the right side, so this term represents south. So these are the modification you should understand. Okay, now we'll go back to the original question. See, holding like this or like this based on the first line. Okay, this sometimes it represents north based on the current direction. If the plus terminal of the battery is towards left side, this will be north. If the plus terminal is that side, right side, this will be south. Only this one, that's it. Second sub question, will the magnet be attracted or repelled? Give the reason for your answer. So first we have to write whether it is going to attracted or repelled. Okay, very simple. North and north, it will get repelled because like poles. This is what we are learning from lower grades, correct? Now we have to write the reason. Because you can start from because. You don't have to write the same sentence again, and the time is very much important when it comes to physics, because here the answers are very simple. You have to take lot of time to understand the question. That's it. So because north, okay, the end A becomes north, the end A becomes north, end A becomes north, and like poles repel each other, and like poles repel each other. If you write this much, that is enough. Our next question, state two ways by which the magnetic field due to current carrying solenoid can be made stronger. How to make magnetic field stronger in a solenoid? So very simple. See, the first one, increasing the number of turns of the coil. See, here most of the students will go wrong how to write. The way of writing the answer is also important. Some students will write increasing the number of coils. Coil is only one coil we have, but increasing the number of turns of the coil, this is what you have to write. Increasing the number of coils is wrong because we have only one coil. The complete wire is one coil. Okay, so here you have to write increasing the number of turns of a coil. Number of turns of a coil or number of windings, any one you can write. That is the first answer. Second one, by increasing the magnitude of current. Okay, we know magnitude of current, that is nothing but the current is directly proportional to magnetic field. That means if the strength of current is increased, the magnetic field strength also increases. So what are the two answers? By increasing the number of turns of a coil, by increasing the strength of a current, or magnitude of current, any one you can write. Our next question, a magnet kept at the center of two coils, a magnet is kept at the center of two coils A and B, is moved to and fro as shown in the diagram given. Okay, here when the magnet is kept between the coil A and coil B, these are the two setups of coil A and coil B. Now magnet is kept in exactly at the center. Now we are going to move to and fro like this. The magnet is going to move to and fro. We are going to make it move to and fro. Okay, like this. Okay, now the two galvanometers shows deflection. State the reason whether x greater than y or x lesser than y. So here this is galvanometer x, this is galvanometer x, and this is galvanometer y. So what do you mean by galvanometer? The galvanometer is a device. We have two functions for this galvanometer. One, it detects weak current. One more, it shows the direction of current. So in which direction the current is flowing, that we can find out, and it also shows the weak current. Okay, it is also used to find the weak current. These are the two functions of galvanometer, but here in this method we are going to use to find the direction of current. The galvanometer is used to find the direction of current. Okay, now here whenever the two coils are there and there is a magnet between these two, now we are going to make this magnet move to and fro. Now here they are asking whether x greater than y or x lesser than y. This is what we have to tell them. So x represents the current in galvanometer x, y represents current in galvanometer y. So in which galvanometer there is more magnitude, that is there is more value, that is nothing but there is more strength. Very simple answer, x lesser than y. Why? Because the current and magnets, keep this in mind, the current and magnet depends upon the number of turns. See, 1 2 3 4, 1 2 3 4 5 6, which has more number of turns, coil B. So coil B value will be greater than coil A. That's it. If they are talking about value of current or magnetic field, coil B is always greater. Why? Because more number of turns. So in this case we are talking about galvanometer, so more current. If they are talking about magnetic field, also more number of turns will have more magnetic field. That should be your answer. In this case we are talking about galvanometer, so Y value is greater than X because more number of turns. Our next question, why does a current carrying freely suspended solenoid rest along a particular direction? State the direction in which it rests. Very simple question. This is what we have found the answer in one of the fill in the blanks question. Very simple. Listen, when a solenoid, okay, whenever we talk about solenoid, it behaves as a bar magnet. Keep this in mind. So why does a current carrying freely suspended solenoid rest along a particular direction? Because current carrying solenoid behaves as a bar magnet. That is the answer for the first sub question. State the direction in which it rests. North south direction, because we know whenever we suspend a bar magnet freely, it always rests in north south direction. We know a solenoid, current carrying solenoid behaves as a bar magnet, so it also rests in north south direction whenever it is suspended freely. That's it. Our next question, what effect will there be on a magnetic compass when it is brought near to a current carrying solenoid? Assume there is a solenoid. Okay, we don't know in which way the current is carrying, and that's why we cannot find the polarity of a solenoid. Okay, they are not talking about the direction of magnetic field, all those things you should not think. Okay, the important thing is whenever you brought a compass, okay, magnetic compass near to it, what effect will be there on this compass? Very simple. The needle of the compass rests in the direction of magnetic field in a solenoid. We don't know the direction of magnetic field in a solenoid because it is not specified in the question or the diagram is not given. So we cannot find the direction of the magnetic field in a solenoid. So the needle of the compass rests in the direction of magnetic field in a solenoid. That's it. So whatever the direction is there, whatever the magnetic field direction is there, thus in the same direction it is going to rest. That's it. Our next question, the diagram in the figure shows a coil wound around a soft iron. So this is a soft iron, the coil is wound around it, that is XY. State the polarities of end X and Y as the switch is pressed. This is a key. Key is nothing but switch. When you press the switch, current flows and we have to find the direction of magnetic field. That's it. They have one more question that we'll talk about later. Now listen, first sub question. Okay, X and Y, which is north and which is south? Very simple. See, first thing, the first line of the wire, okay, the first line of the wire is above the soft iron bar. So you have to hold it like this, because in one of the questions as well as in the concept video we have discussed, if the first, everything depends upon the first line. So whenever the first line is above the coil, okay, above the bar, you have to hold it like this. Hold it like this. Now this represents north sometime or south sometimes, that depends upon the current. If the plus symbol is towards left, so this is plus and this is minus, so the plus is towards left, that means this is north, this is north. Actually we are not supposed to find the answers in this way. Okay, we have to find whether it is anti-clockwise or clockwise. If it is anti-clockwise, it is north. If it is clockwise, it is south. But many students will get confused because this is a 2D diagram. If it is 3D, we can aram say show it. Anyhow, it is 2D. That's why these kind of methods are very useful. Now you have to hold it like this because the first wire is above and this represents sometimes north, sometimes south. That depends upon the polarity of current. So first, if the plus terminal is on the left side, this is north. if the plus, assume the plus is somewhere here on the other side, then this would have been south for this question. Anyhow, the plus is on the left side, so the x is north and the y is south. Don't write it in short forms. Don't write it in short forms. You have to write full form. Then one more question. Okay, suggest one way to increase the magnetic field in a coil. See, we know how to increase the magnetic field by increasing the number of turns, one, and by increasing the current in the circuit. But here the important thing is they have given a rheostat. This is RH, rheostat. What do you mean by rheostat? It is nothing but a variable resistance. Variable resistance. We can vary the resistance. Whenever this rheostat is given in the question, you have to be very careful, because what is the one way to increase the magnetic field of a coil or in a circuit? By increasing the current. But here we cannot increase because they have given the rheostat. How to increase the current value using the rheostat? What is rheostat? Rheostat is a variable resistance. We know resistance, okay, resistance is inversely proportional to current. That means if you increase the value of resistance, the current value decreases. But here what we want to increase the magnetic field, we need to increase the current value. So how to increase the current? We have to reduce the value of resistance. Okay, the current value increases. So your answer should be by decreasing the value of resistance. See, if the rheostat is not given, then your answer should be by increasing the number of turns, or you can write it as by increasing the current in the circuit. But anyhow, the rheostat is given, you have to talk about resistance. So rheostat is given. How to increase the value of magnetic field? By increasing the value of current. How to increase the value of current? By decreasing the value of resistance. By decreasing the resistance value, current will be increased. Because of the current, magnetic field will be increased. Our next question, what is an electromagnet? Name two factors on which the strength of magnetic field of an electromagnet depends, and state how does it depends on the factors stated by you. Very simple question. First we'll write the definition. What is an electromagnet? Electromagnet is a strong temporary magnet made by passing a current in a coil wounded around the soft iron. Okay, wounded around the soft iron. It is also called as artificial magnet. So this is the definition. Then name two factors and state how it does depends. The factors are the number of turns of a coil and the current in the circuit. These are the two factors. How it will affect it? State how does it depends on the factor. Both are directly proportional. Number of turns of the coil is directly proportional to magnetic field, and the current value in the circuit is also directly proportional to magnetic field. So the two factors are number of turns and current in the circuit. How does it depend? Both are directly proportional. That's it. Our next question, state two ways through which the strength of an electromagnet can be increased. Just in the previous question we have discussed, correct? How to increase the strength of a electromagnet? Very simple, by increasing the number of turns of a coil and by increasing the current in the circuit. That's it. Our next question, state two advantages of an electromagnet over a permanent magnet. So we have to state two advantages. See, in the concept video we have learned three. We are going to learn all the three here also. Whatever you like, okay, whichever you feel it is easy to write in the exam, you can write. See, advantages of electromagnet. Very simple. It produces strong magnetic field. The electromagnets produces strong magnetic field. Then the polarities of the magnet. The polarities of the magnet can be reversed by reversing the direction of current. The third one, the strength of the magnetic field can be increased by increasing the current in the circuit. That's it. State two differences between electromagnet and permanent magnet. See, this is a very simple question. This one we are going to skip it. Why? Because there are 5 differences. That is what we have learned in concept video. There is the same question, no logic behind it. That's why we are going to skip it. Our next question, why is soft iron used as the core of an electromagnet in an electric bell? Whether it is electric bell or electric motor or MRI machine, whatever the application they are talking about, the soft iron has one property that they are asking. Okay, why we have to use soft iron? Because it has low retentive property. Okay, many students will write lengthy answer for these kind of questions, but by just stating the exact keyword, you don't have to define it. Okay, what do you mean by retentive property? Retentive property means holding that power again. Okay, like I'll give you an example. Instead of soft iron, if we use any other material, okay, like normal iron only, okay, after you take out the current, when you turn off the switch, the current will be taken out. Even though you take the current out, again it will hold the magnetic property for some time. That is nothing but retentive property. Okay, but why we are using soft iron? Soft iron has low retentive property. Once you turn on the switch, it gets the magnetic field power, magnetic field strength. Once you take out the electricity, okay, that is nothing but current, okay, the magnetic field goes off. Okay, instead of writing all those things, very simple answer, low retentive property. That's it. Our next question, how is the working of electric bell affected if alternating current be used instead of direct current? See, this is the symbol of direct current. This is DC. This is the symbol of AC. Okay. Now, so the question is, in an electric bell, instead of using DC current, what happens if you use AC current? Very simple question. See, assume this is an electromagnet. Okay, so if you pass current through it, this becomes a magnet and there will be a magnetic material. If current passes through it, this will get attracted, the bell will ring. This is what happens in an electric bell. Now, this question is not there in the syllabus. Okay, we are learning because this is not about working. It's about a logical question. What happens when the AC or DC current passes through it? That is important. Now listen, when a current passes, this will get attracted. Correct. Now, if we use DC, this is what happening. Okay, what if we use AC? In AC, the polarity will keep on changing. Correct, polarity will keep on changing. For 1 second, it will change 100 times, 50 times positive, 50 times negative. So, if it is changing the polarity, okay, if it is changing the polarity, what happens here? If the attraction, okay, magnet, this is a magnet, electromagnet, and this is a magnetic material. Attraction does not depend upon polarity. Correct. If you keep, so assume there is a nail, you take a nail and you take a magnet. Okay, magnet. If you bring the north pole towards the magnet, it will get attracted. If you bring south pole also, it will get attraction. Attraction does not depend upon the polarity when there is a magnet and magnetic material. If there are two different magnets, then polarity comes into picture. But whenever there is a magnet and magnetic material, polarity will not affect anything. Even though we use AC current, okay, polarity changes, but attraction of magnetic material to a magnet does not depend upon the polarity, so it still works. Our next question, name the material used for making an armature of an electric bell. Give reason for your answer. The material is soft iron. Okay, soft iron. And in one of the questions we have discussed why we have to use soft iron, not the normal iron or any other material, because soft iron has low retentive property. What do you mean by that? That means if you give the current, it will have the magnetic field. If you take out the current, immediately it will lose its magnetic power. So in other materials, even though you take out the current, okay, for sometimes it will hold the magnetic field, but when it comes to soft iron, okay, it will immediately, okay, turn off the magnetic field. That is nothing but, okay, holding the power is retentive property. Soft iron has low retentive property. That's it. Our next question, by using a compass needle, describe how can you demonstrate that there is a magnetic field around a current carrying conductor. See, here these kind of questions will not be asked, but the important thing is based on this experiment, okay, this kind of experiment, the questions will be created. But this experiment we have learnt in the concept video. This was our first experiment, so that's why we are going to skip it. There is no logical question in this question, just an experiment. We have to describe it. When the current flows from north to south, where will be the direction of magnetic field? South to north, where will be the direction of magnetic field? All those things we have learnt in the concept video. That is our first experiment. Our next question, draw a diagram showing the direction of three magnetic field lines due to straight wire carrying a current, and also show the direction of current in the wire. Okay, very simple question. This is what we have learnt in concept video. Here also we are going to draw, because this is a very simple diagram, and the way of asking the question is different. In the concept video, the question, the concept was very direct. Here they just twisted it in a different way. Listen, we have to, here the important thing is the straight conductor, the straight wire carrying a conductor. Straight wire can be horizontal or vertical, correct? It can be horizontal or vertical, but whenever they don't mention horizontal, always we have to go for vertical. Okay, if they mention horizontal, you have to go for horizontal, because in horizontal also it's a straight wire, but if they don't mention horizontal, we have to go for vertical. So wire, okay, this is the wire, and this is the direction. This is the direction of current. Okay, now here we have to draw three different, okay, magnetic field lines, and we have to show the direction. Listen, whenever the current is going upward direction, okay, to find the direction of magnetic field, we have to use right hand thumb rule. Magnetic direction of magnetic field is always related to right hand thumb rule. Keep this in mind. Right hand thumb rule. Okay, this thumb represents the current. The direction of these fingers represents the direction of magnetic field. So it is towards like this, right? So it is towards. Wherever your fingers are showing that direction, you write it. That's it. Our next question, draw a label diagram showing the three magnetic field lines of a loop carrying current. Mark the direction of current and the direction of magnetic field by arrows in your diagram. So this is also very simple question. Listen, so first write the direction of current. This will give us a hint to write the direction of magnetic field. Listen, whenever the current is going up, see, it's going up, right? You can write this up this side and this down mark this side. Anything is fine, but according to that, we are going to write the direction of magnetic field. Listen, whenever it is going up, okay, whenever the current is going upward direction, see, this is a circular path. Okay, loop, current is going up, the field, magnetic field lines will be towards right side, towards right side. So they are asking three, correct? 1, 2 and 3. You can write, you can extend this one, you can write it like this. And we know whenever we hold right hand thumb rule, okay, this direction shows us the direction of magnetic field lines. If you write this up that side, the same diagram you should write that side. Okay, for below also you have to write 3 magnetic field lines, and we know if it is up, towards right, if it is below, towards left. And exactly at the center, okay, exactly at the center we have to draw a line like this, and the direction of this line also important. See, these lines are going here, going up, and these lines are also going up, correct, going up. So this magnetic field also has a direction that will go up. That's it. So up 3 magnetic field lines, okay, and down, okay, whenever the current is coming from up to down, okay, it's going towards down, I have to hold it like this, and this represents these fingers showing towards left. So towards left, exactly at the center, it is going up. Why? Because see, it's going up, and this is also going up. That's why the center also going up. That's it. Our next question, draw a diagram to represent the magnetic field lines along the axis of current carrying solenoid. Mark arrows to show the direction of current in the solenoid and the direction of magnetic field lines. Okay, now here first this diagram is very much important. Very simple diagram. A soft iron, okay, and coils, okay, the number of turns ordered around a soft iron. Done. It is connected to a battery. positive, negative, and there is a switch. Switch you can mention here or here, anything is fine. What is the function of switch? Turn on, turn off. If you place it here or here, it will do its job. So now the diagram is done. Rheostat, no need to mention because they are not specifying about it, so no need to mention rheostat. Okay, now this is done. Okay, now once this is done, we have to specify the direction of current and direction of magnetic field lines. First we'll specify the direction of current, because positive is here, it goes up, see here, and goes like this, correct? To find the direction of magnetic field, first thing is first line of the wire, whether it is above or below. If it is above, we'll hold it like this. If it is coming from the behind, okay, the first line of wire, if it is coming from behind, we'll hold it like this. Now anyhow, in this diagram you can write like that also, the same thing. Okay, you have to follow the method, that's it. So the first line of the wire is coming above the rod, so you have to hold it like this. This thumb represents north or south, sometimes it depends upon the direction of current. If the direction of current plus is towards left, this will be north. This is what we have learnt in few questions as well as in the concept video. So if you hold it like this, you know why we have to hold it like this. Now if the plus is towards left, this thumb will represent north. If this is north, this is north, and this will be south. So once you find out north and south, the simple thing is the direction of magnetic field lines. We know, okay, the magnetic field lines, now we know this is a solenoid. If it is a solenoid, it is nothing but a bar magnet, correct? In bar magnet, the direction of magnetic field lines will move, see, now whether to write arrow towards right or towards left, that is important. Now listen, if it is a bar magnet, inside the bar magnet it is south to north, inside it is south to north, correct? It's going out now, okay, extend it, okay, inside it is south to north, okay, outside it is going from north to south. This is very much important. Few students will write the arrow marks like this because they know it is always from north to south, but the important thing is whether it is inside the bar magnet or outside. Anyhow, it is a solenoid. Solenoid is nothing but a bar magnet, correct? It acts like a bar magnet. If it is a bar magnet, inside it is, okay, inside it is south to north, inside it is south to north, outside it is north to south. This is very much important. Our next question, the diagram shows a spiral coil wound around a hollow cardboard. See, a spiral wounded around a hollow cardboard, that is A, B. A magnet compass is placed close to it, like in the diagram. So current is switched on by closing the key. When the key is closed, current will be flowing. What will be the polarities of ends A and B? Okay, first thing, now listen, first whether the first line is above the coil, okay, above the rod or behind the rod. The first line is coming from behind the rod, so you have to hold it like this. Now once you hold it like this, this thumb may represent north or south based on the direction of current, correct? See, wherever, when you hold it like this or like this thumb represents north. If, okay, you hold it like this or like this thumb represents north, okay, when the polarity of plus is this side, okay, plus is this side, okay, if the plus is that side, this thumb represents south. See, again I'll repeat, the thumb most of the time, okay, the thumb, see, again I'll repeat, the thumb may represent north or south. If the plus polarity, if right this side on the left hand side, okay, if this plus is left hand side, this polarity will show north. If the plus is on the right hand side, this thumb will show us south. So this is nothing but, if this is south and this will be north, this will be north. See, we can write it above, north. A is north, B is south. The first sub question is done, okay. A is north and B is south. So our next sub question, how will be the compass needle be deflected? Give reason. Very simple question. Listen, first for that we need to write the direction of magnetic field lines. Listen, whenever you write magnetic field lines, we know this is a solenoid. Solenoid is nothing but a bar magnet. Bar magnet, the direction of magnetic field will be from north to south, correct? will be from north to south. So this is pushing the compass needle this side towards left side. Left side is west. So the answer is west. Okay, because the NDA is north, and we know the magnetic field lines, okay, from a bar magnet will move from north to south. That will push us to the west side. That's it. Our next question, you are required to make an electromagnet from a soft iron bar using a cell and insulated coil of copper. See, these are the coils, insulated coil of copper and a switch. See, they are not specified rheostat, so no need to specify rheostat. And draw a circuit diagram to present the process. Label the poles of electromagnet. Okay, so this question can be answered in 4 ways, 4 different diagrams. Okay, we are going to learn everything, so just to make sure you are perfect in this concept. As I told you, these are the 4 possible diagrams. You can draw any one of them. So first we'll go with this one. First we'll go with this one. Now listen. So the bigger one is positive, the smaller one is negative. This is very much important. Plus, minus, minus, plus. Once you write the plus and minus terminal, draw the arrow marks. The arrow mark of current. This is enough. So here also it's going up and coming down, because the plus current always flows from plus to minus. So here minus, so the current goes up and comes down. So here current goes up and comes down. Okay, now this is done. Now it is time to find the direct polarities of magnetic field. Now listen. First thing is whether the first line, this is the first line, right? First line of this wire, this complete wire, this is the first line. Always you start from left side only. Left side of this wire, this wire, this wire. That is what we are going to learn. This is the first wire, correct? So the first wire is above the rod. See, this is above, correct? This is above. See here, the first wire is below. Okay, behind. Okay, here the first wire is above. Here the first wire is from behind. This is very much important. This is what we are going to identify. Once you identify that, see here this first line is above. Once you find this is above, you have to hold it like this. If the first line is above, you have to hold it like this. See, this represents this all fingers represents the first wire. This is going above the rod. If you see a diagram like this, the first wire is coming from the behind of the bar, so you have to hold it like this. The wires are going, okay, coming from the behind of the bar. You have to hold it like this. This is the first step. Okay, so in all the cases, see, first we learn both these diagrams, then I'll teach you how to do with these 2 diagrams also. These are the only possible 4. Okay, now once you got to know where this is above, right, you have to hold it like this. Now this thumb represents north sometime, south sometime. So how to identify? That completely depends upon plus. Where is plus? If the plus is towards left, okay, listen, this thumb, whether you're holding like this or like this, this is very much important. Listen carefully. If you are holding like this or like this, okay, this thumb represents north sometime, south sometime. That completely depends upon the positive terminal of the battery. If the positive terminal of the battery is like towards left, this thumb represents whether you are holding like this or like this. Okay, if the positive is towards left, okay, I'll write it like here. Okay, if the positive, okay, of the battery terminal is on the left side, see, this positive terminal is on the left side. Here the positive terminal on the right side. Okay, then thumb, okay, is north. Thumb is north. Okay, the thumb is north. If the positive terminal on right, the thumb represents south. This is very much important. Listen, see, actually this is not the way to learn it. Okay, it depends upon whether it is anti-clockwise or clockwise, whether these circles are providing anti-clockwise or clockwise based on the direction of current. As it is a 2D diagram, this is very much difficult to understand whether it is clockwise or anti-clockwise. That is why I found a method. Okay, this method works on all the diagrams. I have tried it. Okay, you can also try, and you will also understand while we are solving the theory solutions. Okay, theory questions. Now listen. First, the thing is, plus is on the left side, the thumb represents north. Okay, this thumb represents north. If the plus is on the right side, you see here the plus terminal is on the right side, so the thumb represents south. Now first thing is, you have to hold it up. You hold it like this because the wire is above the bar, above the coil, correct? The first wire is above, so we have to hold it like this, and we have to see plus is on the left side or right side. Plus is on the left side, correct? If plus is on the left side, thumb represents north, so this will be north and this will be south. That's it. See, once you understand this logic, to find north and south will take only 10 seconds. In the exam, once you find the answer for north and south, writing will take 10 seconds. So these kind of questions will be asked for 3 to 4 marks. Within 1 minute, you can score 3 marks if you have the knowledge. That is what we are going to learn here. Okay. Now we'll go for the this diagram B. Okay, for second diagram. Now listen. So this, okay, don't worry about this diagram. See the first line. First line is coming behind, from the behind the bar, so you have to hold it like this. Now this thumb represents north, sometimes south, sometimes, depends upon where is the plus symbol. Plus symbol is on the left hand side, so this thumb represents north, correct? If the plus symbol is on the left, this is on the left, right? So thumb represents north. So thumb is, say this thumb represents north, that means this side is north and this side is south. That's it. The same method we are going to apply here. Now see the first line. See the first line. This is above. First line is above the rod, above the bar, correct? So you have to hold it like this. Now this thumb represents north sometime, south sometime, depends upon the where is the plus polarity. Plus polarity on the right side. Okay, you see, plus is on the right side, minus is on the right side. You hold it like this. So now if plus is on the right side, thumb represents south. If plus is on the right side, thumb represents south. Where is the thumb? That is left side. So this is thumb represents south and this is north. That's it. The same thing here. See the first line. First line is coming from the behind. Coming from the behind. Now the thumb represents north south, depends upon the polarity of plus. So plus is on the right side. Okay, plus is on the right side. If plus is on the right side, thumb represents south. Where is south? South is that side, correct? South is that side. So right, south and north. Okay, see, this concept might be a little confusing for you, so go back and rewatch it. You will definitely understand. This is what very much important, because based on this one, any kind of questions, once you find north and south, they are going to place compass here and one more magnet here, and based on that they are going to ask questions. If you know this much, you can answer any question. Okay, in the exam you can draw any one of these diagrams for this question to get full marks. Our next question, what name is given to a cylindrical coil of diameter less than its length? Here, very important, these are the logical questions. Okay, so here the diameter of the wire is less compared to its length. Okay, if the length is bigger than its diameter, okay, diameter is nothing but the thickness of the wire. Okay, this is the thickness. Okay, if the thickness of the wire, if the diameter is less than the length of the wire, it is called as solenoid. It is called as solenoid. Now few students will get doubt, if the diameter is more than its length. Actually this is not in the syllabus. For a knowledge I am going to teach you. Okay, for the diameter more than its length, then it's called as pancake coil. Pancake coil or flat spiral coil. Pancake coil or flat spiral coil. As it is not in the syllabus, you don't have to worry about it. This is the only possible question. Diameter less than its length, this is the only possible question. Diameter more than its length will not be asked in the board exam, because this is not there in the syllabus. Okay, now listen. So first sub question is done. Second question, if a piece of soft iron is placed inside a coil mentioned in part A and current is passed through the battery, okay, what name is given to the device? See, there is a coil. inside that you are placing a soft iron. Because of that current, magnetic field will be produced and the soft iron will be converted into magnet. So because of the electricity, magnetism is produced. What you call this as electromagnet. Electromagnet. See, this is how you have to tackle the questions. Okay, so electricity is passed. Okay, soft iron is there. Because of that current, electricity, this soft iron is converted into magnet. Electricity becomes a magnet. Electromagnet. Done. Then give one use of the device mentioned by you in part B. Okay, electromagnets. What are the uses of electromagnets? It is used in electric bell. Okay, then the electric motors. Okay, electric motors. Then MRI machines. There are many applications, and loudspeakers also. You can write any one of these things. Our next question: show with the aid of diagram how is a wire wound on a U-shaped piece of soft iron in order to make an electromagnet. Complete the circuit diagram and label the poles of an electromagnet. Okay, so we have to take a U-shaped soft iron. Okay, see, okay, you can write, okay, U-shaped soft iron. See, in some textbook it will be like this. Okay, anything is fine. Now listen, U shape. Now we are going to wound using a circular coil. Okay, now listen. So and we have to connect it into a battery and a switch. Rheostat, if they mention, then you can specify it. You can write the rheostat here. If not, no need to worry about it. So plus and minus. Now here the important thing is, once you draw this much, draw the arrow marks. Okay, draw the arrow marks. This diagram can be write in two ways. Okay, listen, I'll show you. Okay, so the plus. Okay, now listen, this. Okay, this much is enough to I explain the concept. Listen, if the first, see here, the first line is above, here the first line is below, and the direction of current is very much important. Listen, see here in this diagram, the first line of wire is above, so the arrow mark is towards right, correct? This is very much important. If towards right, see, if it is towards right, it is going to produce clockwise. See, if it is towards right, it is going to produce clockwise. We know if it is clockwise, it is south. Anti-clockwise, it is north. The same question. See, the polarity is also same. Okay, here the first line is from the behind. If this first line is from the behind, the direction of current is towards left. If it is towards left, it is going to provide anti-clockwise direction. If it is anti-clockwise, this will be north, this will be south. This is very much important. Complete the circuit here. Okay, so complete the circuit, connect it to the negative part. The important thing is first line. If the first line is above, the direction will be like this, correct? If it is towards right, clockwise. Okay, if it is clockwise, it is south. If this is south, this will be north. In some of the diagram, you have to be very careful. So the diagram will be given on the both side. Okay, see here in this case, right side, and it turns towards the left side, correct? That's why this is south and this is north. In some of the diagrams, both the sides, both the sides towards this is also right, and this side also the arrow, the current direction will be towards right. That means here as well as here, both the sides it is providing clockwise. If both the sides are on the right side, these arrow marks are very much important. If the arrow marks are on the right side, towards right side, both the side it will form clockwise, both the side it will be south and south. Okay, south and south. You might be thinking, how can a magnet have south and south? Very simple. Assume you take a box of iron, assume this is south, north. Okay, you cut into this kind of thing. Okay, this piece. Okay, like this. See, again this remains, as it is south and south and north only. Okay, this part will be north, that side, that's it. Okay, now in the same in the diagram they are going to give, if in the diagram these arrow marks are towards the left side on both the sides. Okay, if the arrow mark is on the right side, okay, it is clockwise. If it is clockwise, south. Okay, if the arrow marks are towards left side in both the cases, see in this side, in this case, in this diagram it is right side. What if the diagram they have given, this side it is left, towards left, this side also it is towards left, then both the side will be north and north. You have to be very careful about it. Okay, if it is right side, towards right side, it is clockwise, that is why it is south. If it is left side, it is anti-clockwise, that is why it is north. Any one of the diagrams you can draw. Our next question, figure shows the current flowing in the coil of wire wound around the soft iron horseshoe core. Horseshoe means U shape only. Now the first question, state the polarities developed at the end A and B. Okay, here in the previous question I have given one hint. Okay, based on the direction. You see, now see the direction. One it is down. Okay, one up. The direction arrow marks. Okay, one side of the arrow marks are upside, one side of the arrow marks are downside. Don't worry about this one. This is the first line. So we have to see which is on the coil. Okay, on this U-shaped magnet we have to see. So don't worry about this one. Okay, here this is facing downwards, this is facing upward. That means one should be north, one should be south. If both the sides are downward, okay, both the sides will have same polarity. If both the sides have upward direction, both the sides will have same polarity. So anyhow, in this question, one on one side, okay, here it is downward, here it is upward, so both the sides will have different polarities. This is the conclusion you should get in the beginning only. Okay, whether you are going to get both the sides same polarities or different polarities. Now how to find this one? That question was like this. Previous question was the horseshoe magnet was like this. Here it is, okay, horizontal, it was vertical in the previous case. Turn it, okay, turn it like this. If you turn it like this, okay, this will, the arrow mark, see now it is here. If you turn it like this, the arrow mark will be like this, correct? So visualize it properly. See, if you turn it like this, okay, in the previous case, if you get a question like this, just turn it like this. So turn it like this, the arrow mark towards downward will, see, once you turn it, this downward arrow mark will move towards left side, correct? In the previous question only we got to know, if the arrow mark is on the, only for horseshoe magnet, if the arrow mark is on the left side, now at this case it is downward. If you turn it like this, it becomes, okay, left side. If it is left side, this will be north, and we know one is downward, one is upward. Obviously we have different polarities. If this is north, this will be south. Our last question, see, this question is based on electric bell concept is not there in the syllabus, that is why we are going to skip it. If it is based on a logical question, I would have taught you this is an experimental based question. Okay, we have to describe the experiment, that is why we are going to skip it. Now we have completed all the theory questions from your textbook. So next thing is, go for the second part of this magnetism, learn all the concept first, then go for its solution. Like this, if you do, if you have numericals after the theory question, just directly jump into numericals, so you will understand everything. If you take an example of any one chapter, concept videos will be done, then immediately go for theory videos. If numericals are available, go for it. Once you learn all these things, everything about a particular chapter, you will get only 90% of the knowledge. Why? Because you don't know how the questions will be asked in the board exam, because we cannot expect the questions from the textbook, correct? So they'll keep on creating the questions every year, so we have to be very much careful about it. The knowledge is the key. Whatever the question they ask, whatever the twist they do, if you have the proper knowledge, you can answer any kind of questions. That's why after all these things, concept, theory, solution and numerical videos, we are going to provide solutions for previous year papers. Not only that, previous year papers will fetch you how the questions you are going to get, but the complete knowledge is based on logical questions as well as application questions. That also we are going to do chapter wise. So once you finish all these things, just directly go to the playlist called previous year papers. There you will get the question as well as the solution. Now we are not just providing the solutions, we will teach you the alternative ways to answer those questions, and the precise answer is enough for us, and we were going to teach you the same question, what if they ask in different ways. All those tricks we are going to teach you in the previous year paper solutions. After that, logical and application oriented questions which can be expected, okay, based on that is also chapter wise. From the chapter 4, what are the questions, logical questions, what are the application questions you can expect, all those things will be chapter wise, so that it will be easy for you to learn. So learn everything, get 80 on 80 without touching the textbook. Thank you.